Welcome to part 2 of tutorial 6. In the first part, we built a complete groundwater model from scratch, following Anaxim's structured workflow. We defined domains, set boundaries, and included essential model elements. Now, in this second part, we'll analyze the model further, refine SVAS spacing, and introduce additional validation checks to ensure good results. Let's jump in. Let's analyze the leakage factor to assess whether our SVAS spacing is appropriate. On the model information display, located on the left side of your screen, toggle to the bottom to locate the leakage factor. Now move your cursor around the model and observe how the leakage factor below changes. You'll notice that no leakage factor appears in the outer domain, since it only has one layer. However, within the site scale layered domain, you'll see a leakage factor below of about 21 meters. Let's recall two rules of thumb from the previous tutorial. 1. Where vertical flow is strongest, such as around wells, SVAS spacing should be 1 to 1.5 times the leakage factor. And 2. In other areas, spacing should generally be within an order of magnitude of the leakage factor. Right now, our SVAS spacing is 60 meters, which is about 3 times the leakage factor. This suggests that we may need more SVAS resolution, particularly in the area between the wells, where vertical flow is highest. To confirm this, let's perform a quick extraction check by comparing modeled extraction to extraction from heads. Both values are displayed in the model information display as you move your cursor around the domain. Start by hovering over the outer domain. You'll notice that while a modeled extraction value is present, extraction from heads does not appear because this domain only has one layer. Now, move into the site scale domain and observe how these values vary. In between the wells, you may notice that modeled extraction is up to 10 times higher than extraction from heads. This difference suggests that we need finer SVAS resolution in these areas. At this point, we have two options. 1. Reduce the SVAS spacing for the entire site domain upper layer from 60 meters to 30 meters. And 2. Add an SVAS polygon specifically in the area where additional resolution is needed. Since I promised to show you how to add SVAS polygons, let's go with the second approach. This will allow us to improve resolution only where needed, without unnecessarily increasing the number of equations in the model. This is how to add the SVAS polygon. We'll start by using the digitizing tool to capture the coordinates for our SVAS polygon. First, go to Digitize, Circle Polygon, choose 10 sides. Then, place your cursor in the center of the well cluster and left-click to set the starting point. Next, drag outward in any direction. You'll see a yellow circle expanding as you move. Finally, once the yellow circle extends past the wells, reaching about halfway to the boundary of the site scale subdomain, left-click again to capture the coordinates. And just like that, we've digitized our SVAS polygon. Now, let's apply these coordinates to the model. Go to Model Input, Area Source Sync, Spatially Variable, Polygon. Create a unique label, e.g. High Resolution SVAS. Under Node Spacing, set the value to 30 meters. Click Edit under Coordinates, then paste the digitized coordinates and smalling. Leave the remaining inputs as default, but I'll note that this is the section where you could add precipitation recharge if needed. Click File and Save. Now let's solve the model again. Go to Solve and wait for the calculations to complete. Then go to Make Plot, all selected features, choose Level Time, Level 1, and click OK. Now let's zoom in for a closer look at the site area and replot the model. First, scroll in until the site scale subdomain takes up most of your screen. Then, go to Plot Input, set Plot to Current View. Lastly, go to Make Plot, all selected features, choose Level Time, Level 1, and click OK. This time, you'll notice a light blue circle around the well cluster. That's the SVAS polygon we just added. Within this area, SVAS points are now much denser, improving resolution exactly where we needed it. Now, let's run another spot check comparison of modeled extraction versus extraction from heads to confirm that our adjustments worked. As you move your cursor around the SVAS polygon area, you'll see that the two values are now nearly identical everywhere. A clear sign that our SVAS spacing at 1.5 times the leakage factor sufficient. Before we wrap up, there's one more check that we discussed in the last video. plotting a transect comparison of modeled extraction versus extraction from heads. This will give us a broader view of how well our SVAS spacing is capturing vertical flow. We'll start by using the digitizing tool to select a transect for analysis. Go to Digitize, Polyline, Measure Distance and Area, and click OK. Within the SVAS polygon, left-click anywhere to set the starting point of the transect. Drag your cursor so the yellow line crosses one of the wells and extends outside the SVAS polygon. Left-click to pin the endpoint, then right-click to record the coordinates. Now that we have our transect coordinates, let's generate the extraction plot. First, go to Analysis, Conditions along a line, Graph Conditions along a new line. Then, paste the digitized coordinates into the line coordinates box. Next, select Extraction, then click Make Plot. You'll now see a curve appear. Your graph may look slightly different from mine depending on where you digitized your transect, but the key feature to check is how modeled extraction and extraction from heads compare. What we want to see is that the two curves are close together. This indicates that our SVAS spacing is capturing vertical flow uniformly across this transect. There's no strict rule on what defines an acceptable match, but if you see a large gap between the two lines, that suggests your model needs more SVAS points in the area where the discrepancy occurs. By using this transect comparison, we can check our SVAS spacing over a large area and ensure we're getting a good representation of groundwater flow. In this tutorial, we built a complete groundwater model from scratch, following the same workflow used for both simple and complex simulations in AnacSim. We established the model setup, created domains, defined boundaries, added wells, and applied SVAS points to refine vertical flow. Then we ran the model, analyzed leakage factors, checked modeled extraction versus extraction from heads, and even used a transect comparison to check SVAS spacing across a prescribed section. In the next tutorial, we'll take things a step further by introducing transient flow, modeling how groundwater levels change over time. See you there.